So in my talk, I wanted to cover sort of where I think SPH is and where I think galaxy formation is and where I think we need to go to improve things. And for that, I wanted to show the blob test partly and talk about where SPH is in terms of good hydrodynamics. And the blob test, of course, came from some work by Oscar Agert and several other people. And this was the AstroSim conference that got this all going. And it's actually similar to Agora in a sense because it was a bunch of people who weren't interested in chest beating but actually working out what the codes did. And so that the tests were developed in a very collaborative way. And that paper had several authors on it, many of whom are involved in Agora as well. And the bottom line was that there was a difference. The SPH codes had a different result to essentially the grid codes, which were all pretty much ppm at that point. And the reason for the difference, well, the fundamental result was SPH blobs were not breaking up. And this is related to essentially effective surface tension. And I show a zoom in of that. In practice, that tends to make the particles line up in rows parallel to interfaces, which tend to suppress Kelvin-Helmholtz instabilities in a way that is quite similar to real surface tension. And there have been a lot of fixes to this. So when this problem was identified, people rushed in and fixed it. In 2001, Ritchie and Thomas actually put forward what's essentially the solution. But of course, following on from Agert et al., Price had a solution. And Justin Reed and his collaborators also have a solution. And recently, Phil Hopkins has presented his solution as pressure entropy SPH. So it's well known how you deal with this. And what I just wanted to emphasize is that the fundamental component in all these codes is a different way of averaging the pressure near the interface when you calculate the pressure gradient. If you do that, then essentially in all codes, this problem goes away. And this is a common component in all these fixes. And so I just refer to this as a geometric density average because each of these fixes has a different name, but this is the common element in each of those. And so if you do the blob test with this in, old SPH has the kind of flying jellyfish problem. But when you put this fix in, it breaks up quite nicely. But I hope you can see that when it breaks up, it's kind of flecky. There's lots of intense points in there. And what's going on there is that even though the blob breaks up quite happily now, there's no surface tension, there is these essentially indestructible low entropy points, right? Whereas we know that the crossing time for that fluid is very short. They should be mixing into the fluid around them and coming to a more average entropy value very quickly, but they're not doing that. So the second issue, which isn't always emphasized sufficiently, is you also have to deal with mixing. And this was actually identified first in the cluster comparison, another comparison project that Carlos Frank and Simon White and others put together based on one of those Santa Barbara workshops. And the outcome of that was something people weren't aware of, which was that the grid codes, and ENSO was the only one which had enough resolution to see this, formed a core. And the SPH codes seemed to have a kind of cusp in the entropy distribution. And how does that happen? Essentially, when you have when you discretize your Euler equations, such as your thermal energy equation, you should be, I mean, when you don't have any substructure modeling, essentially following the entropy exactly. And that's what SPH does. You put entropy on a particle, it keeps it forever. However, when you have a grid codes, you're explicitly advecting thermal energy from cell to cell. That's never exact. Therefore, you mix your entropy whether you want to or not, right? And that essentially is the source of the difference. Now, you could argue what's correct. And what I would argue is what's correct is that we do not have a finite minimum scale. This is only true if you have finite self-enclosed fluid elements that don't interact with each other. When they do, those subgrid terms actually result in an effective mixing. So if you go essentially one order higher than the basic Euler equations, the next term up is a mixing term that all codes should have. And when you put that in, you can get essentially cores to form in SPH simulations. And this is something that we showed back in 2008. However, not all mixing is equivalent, right? There are some subtleties to this. And this is something that Chris Power Justin Reed and Alex Hobbs have explored in more detail, you can't just do whatever diffusion you want. If you really want to get the turbulence statistics correct, you have to be a little bit careful about that. But in terms of crude problems like the blob test, that's all you really need to do. So if I put that in, I can get a nice blob test where I get smooth mixing of my entropy and any other tracer like metals and so on. So this is also important for galaxy formation, that you have this mixing in to redistribute your metals in a correct way and get a good answer. And so if I look at that with an easier to read image using a color scale for the entropy, you can see that qualitatively the ENSO and the fixed SPH, if you like, are very similar. So look at the right-hand panel, the top and the bottom, whereas the old SPH had the kind of flying jellyfish problem. But you could also ask, well, why do we keep looking at grid codes? Are they the right answer? And of course they're not. And that's because your numerical advection errors are not Galilean invariant. They're not actually mimicking the true diffusion at the grid scale very well. And so they actually depend on what you do. For example, in the top version of this run, all I've done is adjust whether the blob is moving through the tube or whether the blob is still and the tube moves past the blob. So in the top version, the tube is flowing all the time. So what happens in this blob test is actually the blob starts moving relative to the fluid, but then it slows down, it kind of balloons and mushrooms and falls apart, and it freezes into the flow. Now at that point, the relative velocities are very small and no more diffusion should occur. However, when the entire flow in the tube is moving, those advection errors continue to apply and you continue to mix, even though essentially the blob is now frozen into the flow. And so in the top version, you can see that ENSO with a moving flow actually continues to mix well after the point where the blob has frozen into the flow. Whereas if you have a non-moving tube and a moving blob, the blob comes to rest when it's fully mixed, and then you freeze in with much more coherent structure left in the blob, which is the bottom panel. So that doing this right is non-trivial, and I'm going to leave that to Justin and Alex to discuss in a little more detail. Now you can do some tricks to improve behavior in grid codes. One problem in galaxy formation, for example, is that you have a massive background advection in your galaxy disks, right? You have 200 kilometers per second circular velocity, and then you have Mach numbers that are quite small, quite high, so that your sound speeds are very small, and so that you're essentially advecting around with a Mach number of maybe 200 or more. And so that these advection terms are enormous in galaxy disks, and some work that we've done recently with Samantha Benincasa, my student in the audience, is to look at how you can improve this situation. If you put a rotating frame on your galaxy disk, then you can take out the 200 kilometers per second, and you can dramatically reduce the advection errors. And so that's the only difference between the left and the right panels up there. They have exactly the same grid resolution. Just in the right-hand panel, we subtracted out the rotation of the galaxy disk, and it improved our effective resolution by a factor of 4 because that excess diffusion was suppressed. So I would argue that we've managed to address a lot of issues, but there is one paper that appeared recently, which is Bauer and Springel, which was raising the issue of subsonic turbulence. So this test involved looking at driven Mach 0.3 turbulence, quite subsonic, and then arguing that AREPO and grid codes and SPH were getting different results, and should we be concerned about this? And this is an image from that paper showing the velocity field, and you can see there is more small-scale structure in the AREPO solution than there is in the SPH solution shown here from work by Daniel Price, which essentially occurred at the same time. So what's going on in the SPH is if you look at Gadget 2, and I'm told that they did something a bit strange. So the Gadget 2 curves here are not standard Gadget 2, but Gadget 2 with essentially SPH from pre-1995. They turned off all switches on dissipation and so on, so it's the kind of dumbest SPH you could do. And you can see that you get quite rapid deviation in your turbulent kinetic energy away from the Kolmogorov minus 5/3 line. If you put in kind of the Balsara switch, so sort of all SPH since 1995, you bring it up and you have a lot less dissipation. And in 96, Morris also suggested a finer switch. And if you add those things, then your dissipation reduces. And in terms of, you may hear claims that I have the most wonderful SPH ever and I can do even better than that. So I put Daniel Price's result on this as well. And you can see that he's managed to do slightly better. But it's sort of, SPH seems to have an issue that it can't really get you to very high Reynolds numbers. In general, grid codes can get you to a higher Reynolds number than an SPH code can, and it's very hard for SPH to reduce its dissipation much below the result shown by Daniel Price here, for example. And you can compare that the actual behavior is correct. The gray line under Daniel Price's magenta line is what should happen in the presence of dissipation, and SPH models a flow with that Reynolds number very, very well. And so where does all that small scale structure come from? In a repo, you can see that in the repo result, they have a large excess of kinetic energy in their solution to this problem, and that is what's called a bottleneck. It's insufficient dissipation, so that when the energy gets down to the small scales in the grid, it doesn't have anywhere to go, and it kind of just bottles up. And this is a common result for grid codes. And so when you plot an image of these simulations, you will always see more small scale structure because you have all this kinetic energy that's kind of just building up there, and you can see that in the result. And so the bottom line, I think, to take away from this is that all codes actually do deviate from the expectation for infinite Reynolds number, but of course none of them can get anywhere near that. And it's more just a question of which way does the deviation go. Are you preserving more of your energy in small scale kinetic energy, or are you converting it to thermal energy according to a different effective Reynolds number? So a way to quantify that is that you can think in terms of what does this fairly unresolved or poorly resolved kinetic energy do. It behaves to leading order like an effective pressure, right? And so if you have a Mach number of 0.3, you're talking about effective pressure of less than 10% involved in this small scale turbulence. All the codes are able to get the large modes correct, so we're talking about the small amount of energy in the very high K small modes. That's a little bit different. So the overall result is that grid codes such as a repo, because they use the same fundamental methods for advection and Riemann solving, tend to be a few percent too high in this extra pressure, and SPH tends to be a few percent too low. Now I should point out that this test is a really hard test, and if you talk to applied mathematicians, they would never use a finite volume method to do incompressible turbulence. They think it's stupid. They always go to very high order spectral methods because they want to very accurately control the dissipation. That's very important, right? So this test is kind of at the borderline of what anyone who does turbulence would consider reasonable. So how does this affect galaxy formation? Well, we have to suck this up at some level. Once you're inside the virial shock, you will, at least for a period, become subsonic. So subsonic turbulence is playing a role. However, in terms of gross galaxy properties, the main function will be to provide an effective pressure and adjust the hydrostatic distribution within your hot halo. And then once you get into the ISM, of course, you can cool and you can get high Mach numbers again, and it's a slightly different kettle of fish. Now, recently, there's been some papers, including Volkersberger and Baron Springel, and they've been making these comments that SPH is dissipating too much, and they think that this is the source of a result in some of their galaxy simulations. However, I would argue that what they're seeing is not a result of excess turbulent dissipation, but actually because Agert doesn't have any of the modern shock capturing switches. You can see that the virial shock and the, just look at the bright red and orange on the right, you can see that the virial shock is much further out than the Eurepo one, and I think it's just because essentially Agert, without any modern switch, is triggering its virial shock too soon, too far out. And that is probably the source. I don't really think it's anything to do with subsonic turbulence because it's a few percent effect. It can't possibly do something like this. And that obviously needs more exploration and more power to them for doing these kind of detailed comparisons. So the bottom line is that SPH Galaxies have no more blobs, but actually I don't think the blobs were a big deal. They didn't actually, we found that when we switched to different versions of SPH, it didn't actually change the accretion rates or any of those things all that much. So even though it looks ugly, it didn't actually change the rate at which you accrete gas and build up mass within your galaxies very much at all. However, the effect that we're seeing now is that now we have better hydra, we have better coupling between the feedback and the gas around it. Therefore, with more mixing, the temperatures go more easily to an average temperature like 10 to the 5 K, right in the middle of the cooling curve, and it makes it harder to have effective feedback. And essentially, this is just the same boat that everyone's in, right? We're all in this situation where we're finding that it's hard to get effective feedback. And Romain Tessier was discussing this with me. Essentially, the way he sees it, you have mixing, you have a lot of gas at intermediate temperatures, a lot of cooling, and therefore you're in a hard situation. This is driving people to essentially crank up their feedbacks to try and compensate. So the outstanding issue from my perspective is it's about feedback, cooling, and mixing. No one is resolving the thin layers where these processes are occurring, and no one's really quantified how bad this is. And to me, this is the really big outstanding issue. I mean, you can do tricks. You can turn off your hydro, because the irony here is that a repo is claimed to have better hydro, but they turn it off. And the point is they're trying to extrapolate to the extreme of infinite resolution. At infinite resolution, these interfaces are very thin, and maybe by turning off hydro, you get there. But these are essentially tricks, right? We haven't really quantified how not resolving these things is affecting our galaxies. And now I want to switch gears quickly to some work I'm doing with my student Ben Keller, which is looking at more effective feedback. So one way to get more effective feedback is just crank up these free parameters. The other one is to look in more detail and ask what's going on. So Phil's talked about the role of radiation pressure and UV feedback, but really we're talking about things at sort of the internal ISM level of velocity, escape velocities. We need something that's a bit stronger if we really want to drive winds. But many people who think about feedbacks think in terms of individual supernovae, whereas when you have a star cluster, what you should really be thinking about is a superbubble. And the superbubble theory has been around for a long time, right? Back in 1988 and going back to Weaver et al. 77 and so on. This is a very well established idea. Essentially, you have a star cluster that is producing both winds and supernovae, and with sufficiently many stars, these things shock and combine and essentially act like a hot thermal bubble. So you don't really have a CDOV phase. That's one of the upshots of this. There's no real CDOV phase. You end up with a pressure-driven snowplow essentially instantly. And then the really open question is, how much do you mass load that bubble, right? And essentially, if you have a pressure-driven snowplow, you really don't get any mass loading. It's almost like a contact discontinuity between the bubble and the surface. So then you have to rely on additional physics, such as thermal conductivity, to move material from the dense shell into that bubble and tell you what the mass loading of the bubble should be. So one thing that's fun about these bubbles is that they're very efficient. You actually end up asymptotically with about 45% of your input energy as thermal energy, just sitting in that bubble. You end up with about 20% as kinetic energy. So if you think about Chevalier et al. And all these standard pictures of individual supernovae, they talk about 5% efficiency, 10% efficiency. When you do it in a superbubble, you can get much higher efficiency and keep that energy around for a long time. And so it's sitting there for 30-odd mega years and driving structure in your ISM. So we looked at the role of conductivity. This is just a quick test just showing how it works and showing that it does indeed lead to flows off the interior of the cold shell. This is the simulation we've been doing as a test case. And it's quite fun because you not only get this dense structure in the shell, but it also becomes unstable to Vishnevich instability, so you can get these fingers pointing out into the medium around it. And of course, it could be even more complicated if you had a lumpy ISM around it. So the simulations we're doing, we want to mimic essentially what we're able to do within a galaxy formation simulation. So we have individual star clusters around 3 by 10 to the 4 solar masses, and we wanted to see whether we could capture the essential behavior of superbubble with this kind of resolution, right? And so this is what we were able to get. Essentially, we just had 10 gas particles mimicking a superbubble initially, but then the thermal conduction evaporates material and it joins the superbubble, and we end up with additional mass. But we were able to get essentially 50% of our supernova energy to hang around for the full 30 mega years and drive turbulence and outflows, etc. in our model. Now this is just a toy model right now. We're in the process of transferring these to more galaxy type environments. And we can get mass loading straight out of this at the level of 3 to 6 times the initial mass of the star cluster that was driving things. The other thing we get out of this is that we get that the bubble temperature is regulated. Thermal conduction goes as temperature essentially to the 7/2 times the thickness of the layer. divided by the thickness of the layer. And so it shuts down very quickly when your temperature drops. So this regulates the temperature of the bubble. So rather than having an unknown temperature, and we can compare this to the work of Della Vecchia and Shea, it's actually regulated to be pretty close to 2 × 10⁶ Kelvin. And as I mentioned, it's kind of fun. You get Vishnek instabilities and so on. But since I'm running out of time, I'll just put up my summary. So Della Vecchia and Shea, I really like their paper. They said that if you put the feedback in a small enough mass, you can get whatever winds you like. But then that begs the question, what is the temperature of that material? They pick numbers all the way from 10⁶ up to 10⁸ for their feedback gas. And it all depends on the mass loading they assumed. We're arguing here that if you put in thermal conduction, that physics sets the temperature for you, takes away that free parameter, and then gives you a useful level of feedback that you can use to model galaxy formation.
All right, questions, actually. So chair's prerogative, I'm going to make the first question/comment, which is to point out there's been a ton of work on this sort of superbubbles and hot gas feedback in the star cluster community.
Right.
And one thing you may not be aware of is there's a severe problem with like the Sillage and Castor and Weaver models, which is they overpredict the X-ray luminosities of star clusters by orders of magnitude.
Right, so the big problem there is that the conductivity, the coefficients are highly affected by by magnetic fields and also potential structure within these bubbles, and so yeah, I agree. There's
physical blowout, but I mean,
yeah,
the problem is
it's tricky.
We know observationally you don't have 50% of the supernova energy sitting in a hot phase because if you did, things would look much brighter in Chandra than they did.
Yeah, exactly. So we want to do blowout cases. Yep.
That connects to my question, really, which is that this is a nice idea, but presumably we can get good observational constraints on it by looking at star forming regions like the So are you raising some of that?
Well, part of the trouble is if the energy starts to blow out, it becomes very hard to follow, right? So we haven't done lumpy cases. That would be our next step, right? To do cases where the energy leaks out fairly early into the bubble evolution. Well, I would argue that if you don't have 10⁴ solar masses in cosmology, what are you doing, right? It's like.
So what, do you have insights on which direction we should go in doing this? How to implement this in the large scale scenario?
Well, I think Joel made this point earlier, right? There's kind of minimum resolution to get certain physics. So you have to make a choice. You're either doing a semi-analytic model at some scale, and we've decided that we're just going to bite the bullet and try and get the resolution so we can follow this directly.
Other questions? So
in these idealized runs where you get 50% of the energy remaining after a million years, so what are you thinking about the cooling?
That just standard metal cooling. There was no cooling shut off, so no. Well, one of the drivers for me is I've never liked this cooling shut-off business, so I'm looking for a way of basically ditching that.
So you have cool gas, so do you have much gas below 10⁴ Kelvin?
We have a lot. Everything in the shell is very cold, 1,000 K or less.
And what do you assume about the cooling to that gas, the cold gas?
It just cools, it's just normal metal cooling. There's no special assumptions. It cools to whatever low temperature it wants. Yeah, the thermal energy in that shell is essentially nothing. Yeah.
Just going back to the first part of your talk, when you're comparing the different hydromethods, you're talking about the grid codes and how there's a big difference if you have the blob moving with the flow of the flow, cooling the blob.
Right.
I've heard it said by Jim Stone that that's really not a fundamental problem with the grid codes, but that if you go to higher spatial resolution, the problem basically goes away and the results can.
Right, exactly. All these codes converge. So if you go to high enough, the trouble is that most of the time we don't have that luxury, right? We are, like the clumps are resolved with 10 cells across, like the VDI clumps, they're 10 cells across. We're always working close to the resolution limit. We don't have, the luxury to throw hundreds of cells or thousands of cells at these things.
Yeah, I think it's sort of interesting thing, but also it's very similar like McMaster calculating how
theory. So the very smallest mode that you have will grow because it's like a combination of traffic mode. And that's then always related to the grid.
Yeah, it's not a very controlled test. I agree.
It's very important.
Yeah.
If you don't have physical perturbations in these test problems, then you cannot control actually. So you set yourself up, you're thinking you're solving this problem, but you actually have an extra term that's a noise term that comes from the discretization. So unfortunately, I think those two problems in particular are very not very useful to compare codes because they build in an extra term that just has to do directly with the discretization rather than the equation that you solve.
I agree, but it is
Age with finite perturbation then?
it is but it does grow exponentially, right? So I agree with you. It doesn't matter. You know, it could depend on exactly how you start, but it's exponential growth. So they take over very quickly.